So Dr. Gold, the floor is yours.
Great, thanks so much, Chelsea, and thanks so much for having me. I'm Dara Gold. I'm a data scientist with the Metric, Geometry, and Gerrymandering group. We are a research center at Tufts University. We're in their Tisch College of Civic Life, and we're run by Professor Moon Duchin, who's a math professor at Tufts. We're made up mainly of mathematicians, computer scientists, and geographers, and we look at issues in US redistricting and gerrymandering and in voting more broadly. So I want to talk to you a bit about what we do and particularly about the data challenges we have. The slides are not going again. Okay, there we go. So I'm going to be talking, first giving a brief overview of what partisan gerrymandering is and a bit about some of the recent case law. I'm going to talk about why sampling random district maps is essential to our work and some of the techniques we use for doing that. And I'll focus at the end on the data lift and the data challenges we have. So what is partisan gerrymandering? Partisan gerrymandering is intentionally manipulating district lines to favor one political party over another. So in this example, we have 50 precincts, 20 are red, 30 are blue, and we want to partition them into 5 districts. So here's a few ways we can do it. One is we can partition them vertically like this, and we'll have 3 blue-dominated districts and 2 red-dominated districts. We can partition them sort of horizontally this way. Again, we have to have 10 precincts in each, and we'll get 5 blue-dominated and 0 red-dominated. Or we can partition it this way and get 3 red-winning districts and 2 blue-winning districts. So in this last case, only 40% of the districts are dominating 60% of, 40% of the precincts are dominating 60% of the districts. So that's sort of a simple example. So here are some real world examples of gerrymandering that I'm sure a lot of you are familiar with. So in North Carolina, which is about 50-50 Democrat Republican voter share, their congressional map was struck down in 2016 as being a racial gerrymander. So not a partisan gerrymander, but similar principles apply. And in particular, this District 12 was challenged. It's considered one of the most gerrymandered districts in the country. This district was designed to pack African-American voters so they would be able to carry this district, but not be able to have a majority in any districts surrounding it. In the map that North Carolina had to draw to remedy this map or to fix this map after it was struck down, the Republican legislator who was leading the process famously said that he wanted to draw a map that would elect 10 Republicans and 3 Democrats, only because he didn't think it was possible to draw one that would be 11-2. Another case that you are probably familiar with is a case in Maryland where Democrats were accused of gerrymandering their congressional map. Maryland is split about 63-37 Democrat-Republican, but this map elected 7 Democrats and 1 Republican. And in particular, Democrats tried to flip a particular district, their congressional District 6, which had historically voted for a Republican, and they flipped it to vote for a Democrat. So the Supreme Court has never struck down a partisan gerrymander. There's been a handful of cases that have made it to the court over the last several decades, but the court's never been able to say when a partisan gerrymander has just gone too far, and they've largely said that these cases aren't justiciable because there's no standard or measure or metric to definitely say when a map has been too partisan gerrymandered. So for example, there was a case out of Pennsylvania in 2004 where Republicans again were accused of gerrymandering their congressional map. A plurality of the judges said this case wasn't justiciable because they didn't have a standard to really judge it by. And Anthony Kennedy, when he was still on the court, he agreed with the decision, but he famously said that no such standard has emerged in this case, should not be taken to prove that none will emerge in this future. So sort of this invitation for people to still try to come up with a way to measure these partisan gerrymanders. However, last summer in Rucho versus Common Cause, the Supreme Court decided they never will be ruling on a partisan gerrymandering case because they didn't feel they had the standard yet to do it, and that they didn't want to be sort of playing politics and getting into the business of deciding elections in these sorts of cases. So this case was a combination of the North Carolina and the Maryland ones we talked about. They were consolidated in this. However, the fight continues and will continue in state courts. So sort of wrapping up the North Carolina saga, right after that Supreme Court decision, North Carolina Supreme Court finally struck down the congressional map as being a partisan gerrymander, and they had to redraw the map. So we expect these sorts of challenges to continue in state court when states start redistricting in the next couple of years. So even though the Supreme Court decided to opt out of hearing these cases, this invitation that Kennedy put out there to come up with metrics to determine when a map is partisan gerrymandered, it prompted mathematicians and social scientists in the last number of years to start proposing these metrics. So here's a couple. I wasn't planning to go super under the hood with these. I just wanted to give a flavor of what they are. So in 2007, deviation from partisan symmetry was proposed. So this is the idea that given a district map and a distribution of voters, if Party A would get X% of the seats from Y% of the vote, would Party B get the same if the scenario were reversed? So that's sort of one measure. The most well-known one probably of the last few years is the efficiency gap. So that was proposed by Nick Stephanopoulos and Eric McGee in 2015. And that tried to measure this idea of wasted votes, or another way of getting at hacking and cracking. So if one party is kind of packed into a couple of districts where they can carry the district vote, but then they're cracked into several other districts, then they won't be able to win a majority anywhere else. And that's an idea of packing and cracking. Declination, a little less well-known, that came out a couple of years ago, and that measures how quickly a party's vote share jumps district to district. So in that packing and cracking case, if a party is kind of thinly distributed across several districts, their vote share might be really low there. But in districts where they're packed to get a majority, then their vote share would jump up in those districts. And so that's, again, a way of getting at this packing and cracking idea. All of these metrics apply to a single map, so they don't take into account like different political geographies of state to state. So it's really hard to come up with a universal cutoff of when a map is gerrymandered or not, just based on these scores. So for example, a map that has a 2% efficiency gap in one state and a map that has a 10% efficiency gap in a different state doesn't necessarily mean the 10% one represents a gerrymandered map. It could just mean that typical maps in that state have a high efficiency gap because of how voters are distributed, or even some weird geographic features. So we really need a way to look at what's typical in a state in order to say if a particular map is an outlier compared to its own baseline. So the math community converged on this method called Outlier Analysis that tries to do exactly this. So Outlier Analysis is the random sampling of a baseline map collection against which you can compare an enacted map. So the idea is to generate thousands or millions or billions of alternative district maps that bake in a state's unique political geography or any other features, and use that as a baseline to judge a challenge map. So this has been cropping up in a lot of math circles that study this. So for example, this picture on the left is, let's see if I can, okay, this was produced by a group at Duke led by Jonathan Mattingly. This was again an analysis in North Carolina, and they generated 24,000 random North Carolina district maps that all follow North Carolina's basic redistricting rules, so they are, at least valid in some sense. And they, in each map, they counted the number of districts that would have gone Democratic according to a couple of different partisanship measures. And they looked at the two gerrymandered maps that we've talked about, so the racial gerrymander and the subsequent partisan gerrymander. And they saw in those maps were outliers compared to the ensemble or collection of maps that they generated. So as I mentioned, every map when you're doing an ensemble has to adhere to a state's districting criteria, or else it wouldn't really be considered a valid alternative for your baseline. So those maps need to have districts that are equally populated, which is a federal law. If your state really values district compactness, that should be represented in your map sample. Some states really value not splitting counties or municipalities when they're drawing precincts. So if that's the case, your map ensemble should reflect those rules. And in that sense, you have a more valid baseline. So this method has already been used multiple times, so in federal and state litigation, and we expect it to continue on in cases after the next redistricting. Here's one more example of where it was used in court. In the same North Carolina case, Moon Juchin, who runs our group, submitted an amicus brief along with this whole group of mathematicians and other collaborators. It was called the Amicus Brief of Mathematicians, Law Professors, and Students. And in this brief, they also ran their own outlier analysis, and they measured something slightly different. So they made this huge map collection, and in every map, they looked at the district that contained the city of Charlotte, and they saw how democratic that district was. So that's what's on the x-axis here, just how democratic the district that contained Charlotte is. And in the 2016 plan that was being challenged, we can see that Charlotte was much more packed with Democrats than anything else that was coming out on the ensemble. So it's a really striking result. It was not the only amicus brief that endorsed this method. There were a couple of others that also talked about outlier analysis. Justice Kagan, in her dissent from this opinion, cited this brief and really talked about how this method is manageable, and because it has already been used so many times in the lower courts. Okay. So how do we make all of these sample maps? So how do we get this huge baseline of maps against which to compare an enacted map? So going back to this picture we saw in the beginning, we can think of drawing district maps as a partitioning problem. So we have here a bunch of precincts, and we want to partition them into districts. So in this case, we have n geographic units. Our n is 50, because we have 50 precincts. And we have k districts. Here our k is 5, so we have 5 districts. And the total way just to put n units, or 50 units in this case, into 5 districts is 7.4 times 10 to the 32. So it's a giant number of ways you can partition these precincts. Of course, not all of those are valid. So for example, one of the biggest constraints in redistricting is that districts generally have to be contiguous, meaning they have to be connected. I can't put districts or precincts here and make those a district, because they wouldn't be connected to each other. So that cuts out a ton of options, but this whole collection of possible maps is definitely not enumerable. And this is a really small example. This is 50 precincts into 5 districts. In Texas, Texas has 9,000 precincts and 36 congressional districts. So this problem is just, it explodes, and it's not possible to enumerate the whole space or get every map possible. So instead, we want to sample from this space and get a representative sample of alternative maps. So how do we sample district maps? What does that even mean? Here is a map of Iowa's congressional districts. Iowa is the only state that requires their congressional districts to be made out of whole counties. So it has 100 counties and 4 districts. And if we want to make a new map, what do? So we can take 2 of the districts. So we took the right 2 here and reconfigure them. We can do that again, and we can keep making one new map after another based on the old map, and sort of make this chain of maps as you go. We can randomly construct a new district map from an old one, and continuing on in this way, we can collect maps into our big random sample of maps as we go. So how do we actually propose these maps? What's going on between steps 1 and 2 and steps 2 and 3? So we want to start answering that by considering a collection of precincts. So here we have just 12 precincts, not colored, and we can think of it as a mathematical graph object. So that means a collection of nodes or vertices and edges that connect them. And to make this graph based on some precinct map, we want to say each precinct is represented by a node, and two nodes are connected by an edge in the graph if they're adjacent in the precinct map. Okay, so let's say this precinct map is divided into 2 districts with 6 precincts each. We can represent that on the graph structure. So now there's just 6 nodes in each of the districts. So what can we do to randomly configure this into a different 2-district map, now each with 6 nodes again? So we can start by, again, merging those 2 districts together the way we saw them in the beginning. And we can construct what's known as a spanning tree on this graph. So a spanning tree is it's a subgraph that contains all of the vertices. So all of the vertices are still touched by some edge. But a property of a spanning tree is that you can't start from a node and walk around and return to that node without backtracking. So that's not true in the original graph, right? I can start here with a node and then walk around and return to that node without backtracking. That's called a cycle. So a spanning tree doesn't have any cycles. But another one of its properties is if I cut out one of the edges, it will disconnect this graph into 2 pieces. So if you just want to take a second and see if there's an edge here that you can cut, that would leave 2 pieces with 6 nodes each. That's what we want for our new map. And I'm sure you all found this edge as the one to cut. And if you cut this one, we have 2 pieces, 2 disconnected pieces with 6 nodes each. And we can use that to define a new 2-district plan. Okay, so let's apply this idea now. We call this, by the way, the recom algorithm or recombination algorithm. So let's look now at how this applies to a whole state. So going back to Iowa and its 100 counties, I can represent this precinct mapped again as this graph object. We call it a dual graph of the precinct map. So each precinct is represented by a node and they're connected if the precincts are adjacent in your map. So going back to Iowa's 4 congressional districts, I can now represent it as the graph object. So now each of the nodes are colored to correspond to their district. And I can randomly select 2 adjacent districts. So in this case, we randomly select the right 2. And we can apply the spanning tree operation under the hood on the graph object of those districts that have been merged. And we can construct 2 new districts made out of those. And we can continue doing that, selecting 2 districts at a time, and then doing our spanning tree and our split, and keep getting new maps of Iowa as you go. And again, we're only doing splits that adhere to districting rules. So in this case, in real life, we have a certain number of people that live in each of these precincts, and we need to keep the total population in districts equal. So we're only allowing splits that keep population equal. But we just kind of did this walk collecting these Iowa maps, and this random walk takes place in this big abstract space of all of the possible maps of Iowa that we could make. And again, this is this huge space that we can't enumerate, but we're trying to sample from. So what we just did is we started with a map in Iowa, and we took this random walk in this big abstract space, and we were collecting maps along the way as we went. So that process is known as Markov chain Monte Carlo sampling. So that's the methods we use to sample maps. And you can guide the walk in your big abstract space of all maps to move towards maps that we're interested in. So for example, we want to move towards maps that adhere to Iowa's districting criteria. Or if your state really cares a lot about finding districts that are very compact, you can upweight that in your walk. But ultimately, if your chain is set up if your markup chain walk is set up in a particular way, you're going to end up sampling maps from a distribution that upweight the qualities you want in a districting map. So if we keep going, we can pull large samples of these maps to get that big baseline ensemble. Okay, so as you're going and as you're making these new maps, we need to keep a lot of data tracked with every map. So for example, if I wanted to track the number of Democratic seats coming out of all of my random maps, I need to have partisanship information attached to all my districts as I go. Which we do, we need to track that all of our districts have equal populations. That means we need to track demographic data. We want to track all of this at the precinct level because that's the building block we're using to make districts, at least in our case. You don't always have to use precincts. But I wanted to talk about the factors that go into the data lift because it can be extensive, and I wanted to look at New Mexico as a case study as we go. So New Mexico has 2 million people, about 40% white, 46% Latino, and about 8.5% Native American. They have about 1,500 voting precincts. They have 3 congressional districts, 70 state house districts, and 42 state senate districts. So we'll be focusing here on the 70 state house districts. Okay, but what do we want to know map to map as we are making this big map collection? So first, this might seem obvious, but we need to know the map of all the precincts, so where the precincts are and their boundaries, because as we're making new districts, we're aggregating different sets of precincts, so we need to know where they live. We want to attach election returns precinct by precinct, because that's going to be our measure of partisanship. We want to attach demographic data, so number of people by precinct, but also broken down by race for certain analyses you might want to do. We also want, what's often useful is to know which precinct lived in each district in your enacted map. And that could be because you want to compare that map to your ensemble. It could just be interesting to know visually how your starting map compared to a lot of the random ones you're seeing. So that's another kind of piece we want stuck on. So the first part of the data lift is getting your precinct map. This is actually can be one of the hardest parts of the process and can be sort of a showstopper if we can't get this to analyzing a new state. So precincts are stored in precinct shapefiles. A shapefile is just a digital format to store geographic data. Geographic features, so by feature here I mean each feature is a precinct. They can be stored as points, lines, or polygons. So in this picture of a shapefile, they're all, each feature is a polygon. And shapefiles carry around information about each of the features or each of the precincts. So for example, I can highlight one precinct and look it up in what's known as an attribute table, meaning it stores attributes of each of the precincts. So here I've just highlighted which precinct we're looking at. And we're carrying around information like its name, its precinct number, the county it lives in. And we're going to be appending lots of other data to this, like election returns and demographic data. So the precinct shapefile is absolutely essential to what we're doing because without it, we can't recombine these precincts and make new districts. The precinct shapefile, though, can actually be very, very hard to get. So data management varies really widely across states. So we kind of refer to top-down states versus bottom-up states. So for example, Minnesota, another one's North Carolina, has really centralized and really organized management of their election and redistricting data. So for example, if a county changes its precinct lines, boundary lines, they have to report that to the Minnesota Secretary of State within a month so that the Secretary of State's office can update their profile, their shapefile. And you can go and just download the shapefile from the website. So that's considered a very, very organized state and with really good data management. Another state, on the other end of the spectrum, states like Ohio, we call them bottom-up states because counties and municipalities really run the show with their elections. They define their precinct boundaries, but there's no requirement that they're reported up centrally in the state. So county to county, there's different technological capabilities. There's different standards for recording and tracking their precinct lines. And so if you want to do an analysis on Ohio statewide, you somehow have to stitch together information from all the counties, which we'll talk about. Other states are somewhere in between, like in California and New Mexico, which is what we're looking at. In these states, some data or redistricting data and GIS data for the state are housed at universities. So in California in 1993, the state legislature passed a law that said that their redistricting database would be housed at UC Berkeley, which it still is today. And they have a ton of rich information on census data and other redistricting data down to many different geographic layers all in this database. In New Mexico, they call it a data clearinghouse, and that's housed at the University of New Mexico. So that's a really helpful resource in these states. One of the problems which we'll see is that shapefiles or data maintained at these universities might not be totally up to date with things like precincts as recorded by the Secretary of State for a given election. So not all of the resources might be totally in sync. So going back to the Ohio situation, we hosted a summer program a couple of years ago. It was a data summer program for students to sort of learn about what we do. And they took on trying to make a unified Ohio precinct shapefile for the whole state. And as I said, the standardization, or really there is no standardization county to county in Ohio. So students had to end up calling 88 county offices. They had to clean and merge shapefiles from 46 different counties. They had to digitize and merge files from 45 counties, so when they didn't have any shapefiles at all. And they had to approximate boundaries for precincts in 7 counties. So they made this collage of some of the data that they had from every county making up the whole state. And I just zoomed in here on this one county they had to call and ask for their precinct map. And they mailed them, like not even email, they mailed them this paper copy of their precinct map. And so students then had to scan this in and digitize it and make their own precinct shapefile just for that county, and then deal with similar sorts of issues for all of the other counties, and then stitch those together into a Ohio-wide shapefile. So this is, again, one end of the spectrum, whereas in Minnesota, you can just download the whole state shapefile in 3 seconds. So really different state to state. But in New Mexico, once you have your precinct shapefile, the next, I guess, most time-consuming piece of the data process is attaching these election returns. And again, we need that so we can get the partisanship of each precinct and therefore the partisanship of each district in the maps you're proposing. So this New Mexico precinct map I've now colored by county. So for example, this hot pink county is composed of these 5 precincts. If you go to the Secretary of State's website, this is exactly what their election returns look like. They're just in CSVs, and each row is a county, and this reports the number of votes for each presidential candidate in 2016 from that county. So that's good, but again, we want to drill down and get these returns attached at the precinct level, because those are our building blocks for districts. So let's throw in on one county. This is Lincoln County. And the Secretary of State's website also has precinct returns, or returns by precinct. So one of the issues we saw, which is very common, is that in the New Mexico shapefile, which again is from University of New Mexico, there's 21 precincts. But in the list of returns for Lincoln County on the Secretary of State's website, there's 22 precincts recorded. Why does that happen? Again, these are from different data sources where the shapefile might be not updated to match the precincts that were actually used in this election. So what do? We need to kind of look and see what's going on and where this discrepancy arises. Otherwise, we don't know exactly how to attach all of the precincts to the precinct returns to the shapefile. So if we zero into this part of the county, this is just a blown up piece of that part. This is a piece of the precinct map from Lincoln County's website. It's just a kind of where to go to vote sort of map, and most counties have these on their websites. So check to see if you can see where there's an extra precinct that popped up here on the right. So I'm sure you all found that this precinct that sort of looks like this wizard hat or something spawned a new precinct. It was split in half during the 2016 election. So what do you do to fix this? You literally go into that CSV from the Secretary of State and just merge those two rows. So the process is really this tedious, and there's not a good way to automate it state to state. It's really going into each county and checking maps, or I should say there's not a good way to automate it when the data really isn't standardized. So you'd have to go into any county that has these sorts of discrepancies and fix it by hand. In New Mexico, it wasn't so bad. There were only a handful of counties that had this problem. But you can imagine in places like Ohio, where you're stitching together shapefiles county to county, they might not even be all from the same timestamp, how arduous this piece of the process can be. Once you have attached your partisan data precinct to precinct, though, you have this kind of rich new layer of data on your precinct shapefile. And this map here, it's based on 2016 presidential returns, but it looks at the share of the votes in each precinct that are Democratic or Republican, and that's how we color this map. The next part of the data lift is attaching demographic data to each precinct. So the number of people and then broken down by race for each precinct. So here are New Mexico's about 1,500 precincts. Here's New Mexico's 168,000 census blocks. So census blocks are a census level of geography. It's the smallest geography that the census releases their demographic data on. They don't perfectly nest into precincts necessarily, and more importantly, precincts are drawn by the state or by the county, and blocks are created by the census. There is a way for states to sort of recommend what census block boundaries should be to the census, but the point is they're different units kind of overseen by different parties, and we somehow need to rectify them to get demographic data onto the precincts. So here's a picture of a piece of the census block shapefile that's overlaid with the precinct shapefile. And so I just highlighted one precinct zoomed in red, and these are all of the census blocks that live in it in the background. And so once we have that, we can aggregate up all of the people that live in the census blocks and get a sense of the demographics for the precinct level. So once you've done that, now we've added a layer of information to our precinct shapefile. And I'm showing here on the right, in this picture, we see the Native American share of precinct population, precinct by precinct. We can do the same thing for the Latino share and the white share. And so now we have all this extra data traveling around with our shapefile. And lastly, we wanted to attach information about enacted maps to our precinct shapefile. So we wanted to know for each precinct, which state house district does it live in? These district boundary shapefiles are all available from the census website, their Tiger Line shapefile program. I should have said the block file, the census block file is also. So this is a relatively easy part of the data process. You can just download the shapefile, overlay it again with the precincts, and see which precincts live in each district. So here in the picture on the right, you can still see the outline of precincts sort of in white in the background, and then these thick dark lines are the state house map overlaid onto it. Okay, so now we've attached everything we wanted to the precincts. We have partisan data, demographic data, and enacted map data. And so now when I construct a district that's made out of these precincts, I have all of that data now aggregated to the district level. So this is a picture of the partisanship of the enacted state house map. But more importantly, for what we're doing, we can get this district-wide information for any district and any map that we propose. And that's what we're interested in, because that's the process of sampling. We're making map after map of these new districts, and now we can actually assign data to them. So here is a video. Excuse this watermark. I use like the cheapo video converter. But it shows this sampling algorithm in real time. And at each step, you're choosing two districts and doing your spanning tree operation under the hood. And for your new district, I can evaluate its partisanship because I have it all now at the precinct level. So I'm just comparing, I did 300 steps in that video. So this is step 1, the enacted map, and this is step 300. And you can see the maps bear, the district lines, I should say, bear very little resemblance to each other. Of course, partisanship in different regions of the state are basically the same because the underlying precincts haven't changed, but the way you aggregate those precincts makes a huge difference. So here, for example, we have a dark blue district, which doesn't appear here because of how the precincts are aggregated in these two maps. So I let this algorithm go for 20,000 steps. And made these histograms, which again, this is now a baseline collection of maps for New Mexico, and you can evaluate the enacted map against all of these. So in this plot on the left, in every map that we just made, we can see how many Democratic districts there are. And I've plotted here the enacted map in yellow. We can see that it's not an outlier compared to this group of maps. Similarly, we can do the same for the efficiency gap. So remember, the efficiency gap was one of these measures that was proposed to identify a gerrymander. It looks at this idea of wasted votes or packing and cracking. And we can see that the enacted map is sort of right in the middle of all of these scores coming out of the maps. So again, I wouldn't conclude from here that New Mexico, had no gerrymandering involved in their map. You want to look at a whole suite of metrics and the circumstances on the ground, but this is sort of the flavor of how outlier analysis would work. Okay, so a few points that we've gone over. The fight against partisan gerrymandering, we expect to continue in state courts. So states are going to be redistricting after the decennial census data comes out sometime next year. And we expect lawsuits to basically start right after that. And a lot of them now will probably be in state courts. MCMC sampling is becoming the norm in identifying gerrymanders. It's been used in state and federal court, and the methods are still being developed. It's an active area of research. But this lack of data standardization across states and even across counties within the same state will still continue to pose a lot of challenges in this research, as we've seen today. So thank you very much. Please feel free to reach out with any questions we don't talk about today. And our website, mggg.org, has a bunch of our reports and also some graphics, like interactive graphics, that cool things that you can look at, like the space of all possible districting plans and other tools to help make some of these concepts come to life. So thank you again.
Thank you so much, Dr. Gall. That was a really great talk. And I'm grateful for the opportunity to learn more about what you all do over there. So we do have a few questions coming in through both the Q&A and the chat window. Would you like me to field some of those, or would you like to review those?
Okay, sorry, I'm just taking a look. Okay, so I'm getting a question here about how often redistricting occurs. Mm-hmm. So in most states that occurs once every 10 years. It's after the census data comes out. Some states allow mid-decade redistricting, but in most it only happens once every 10 years. So the census data, it's a bit up in the air when it's coming out because the COVID timeline for the census is delayed about 4 months, we're expecting. But after that comes out, that data first goes to the president to apportion the number of U.S. House representatives each state will have, and then census data at the block level and all sorts of geographic unit levels are going to the states, and they use that to actually redistrict their maps. So that would be towards the end of next year to then be used in, I think, the 2022 elections in their states. Let's see.
And on the topic of this type of redistricting, we have another question that asks, what tools or techniques do you recommend for states like Michigan that are using citizen redistricting commissions to draw maps? Is there a way that those commissions use methods that you're describing?
Yeah, so that's a really good question. There are several states with independent redistricting commissions. Arizona and California were two of the earliest ones, and like you said, here, Michigan and also Colorado voted on ballot measures to adopt independent commissions in 2018. So that's really exciting development. I think the vision in our group is that commissions will involve kind of outlier analysis consultants who can see as they're drawing maps if they're drawing things that are unintentionally way off of a state's baseline, which isn't necessarily always bad, but it's probably good to know kind of when proposing a map if it deviates in really strange ways from other typical maps in the state. There's probably a lot less of a chance in that when it's an independent commission than by a state legislature who's kind of openly using partisan motivations to draw their maps. But we're definitely hoping to see these methods integrated even with commissions.
Thank you.
And seeing one come in about, yeah, so about concerns with the 2020 census being prematurely suspended. Yeah, so the census requested from Congress a 4-month delay in collecting and reporting their census data. So usually that data goes first to the president at the very end of the year and then out to the states by April, and they requested a 4-month extension. And then they very suddenly and without much explanation reversed that request in August and said they wanted to rush it by the end of the year. And now that's being sort of held up in court. So it's a little unclear what's going to happen. But yeah, there's definitely a risk of an undercount in this situation, and undercounts, as you would expect, disproportionately affect poor communities and communities with a big immigrant population. So, you know, redistricting data in the census, or the census rather, is used to determine how many representatives a state sends to Congress. And so in states like Texas or Florida with a big immigrant population, that could result in getting less seats than they ordinarily would have if everyone was counted. So that's a big problem.
I'm also seeing a question or two on the bottom-up management states that you were describing earlier. So since I see 1 or 2 of those on there, shall we? So this one says, I'm in one of those bottom-up management states, and I'm interested in learning whether there are any nonprofits or other organizations lobbying state houses to improve the state of affairs. Do you know of anything of that sort?
Oh, that's a really good question. I'm not sure, I'm sure there are. I'm just not sure off the top of my head of organizations that are particularly lobbying on the state of the data. I know sometimes our group is asked to comment on ballot language that's being proposed in different states for just redistricting reform in general. And one thing we try to do is include things about data standardization. But I'm not sure of groups offhand that like specifically focus on data lobbying. A lot of it is just a lot of counties who are reporting up election results just aren't always told what it's being used for. And so they might have different ways to report data, and they just might not know that reporting data in a CSV rather than a PDF, even just things like that, would be more useful for this sort of information being used in research. And through nobody's fault, there's just not a lot of communication coming down from the Secretary of State. So yeah.
The other question that was related to the bottom-up management states is what it pertains to whether or not there are ever any conflicts in states claiming different boundaries. or claiming some of the same places within their boundaries. Have you encountered this issue, or are there ways of solving that issue of conflicting information?
Let's see, conflicting information.
Coming from the county level, in these cases of bottom-up data management.
I'm not sure I've heard of conflicting information about like different precinct boundaries being conflicted coming up from the county level. What I have heard, a different source of conflict is states reporting of their precinct boundaries, and then the census's version of those precincts called VTDs. And so the census puts out, for participating states, shape files of kind of precinct approximations called VTDs. And if the state isn't communicating with the census, those can be really different and not updated for how a state is reporting their own precinct lines. Mm-hmm. So that's another reason why we can't just use the census data for precincts.
Thank you. So we have about 2 minutes left, and I know we have several other questions in the Q&A. So I'm sorry we won't be able to get to all of them. We do have to end this webinar just a few minutes early so we can make space for the ones coming after. Are there any last questions that you'd like to highlight, Dara?
I guess I've seen a couple questions about other things we do in the lab. And I should just say, please feel free to reach out at jara.gold@tufts.edu with any additional questions. I'd love to talk. I've seen some questions about other things we do in the lab. So we do a lot on the pure math research side. So again, map sampling. We do a lot with cities who have commissioned studies of their election system. So for example, if a city either has been sued or it's placed that might be sued for having a discriminatory election system, we might be asked to do an analysis of election system alternatives. Like, what would a districted system look like if a city council is currently using an at-large system? And we can use our sampling methods to come up with all sorts of districting plans that they could use. We might, in the same city, look at what a change to ranked choice voting would look like. And we have a lot of simulation tools to look at potential outcomes in RCV setups. So we do a lot on the ground with that, and then we do a lot of speaking and outreach, like the state affair. So yeah, thank you so much for having me, and please feel free to reach out.
Yes, thank you so much. We really appreciate your time today.
Take care.
Thank you, you too.